Right, so basically this problem, which is 5.7, is a problem involving Dalton's law of partial pressure. Dalton's law of partial pressure. Right, so you have a bunch of different gases, whether you have 3 gases or 300 gases. Okay, each gas will exert its own partial pressure. No matter how many gases that are inside this container. So what is that partial pressure? Okay. Right. This would be for gas 3, but it could also be for gas 2, gas 1, or gas 300. That partial pressure is the number of moles of the gas divided by the total. Okay, so number of moles of the gas divided by the total, that's just a fraction. Okay, so this is a fraction. Okay, fraction of the gas that's in there, inside the container. Remember, part over whole, and this is the total pressure of the whole container. Total pressure of the whole container. Total pressure of the whole container. So like that, this is the partial pressure of gas 3, the partial pressure of gas 2. What would that be? Okay, the number of moles of gas 2 divided by the total number of moles in the container. You multiply that fraction by the total pressure inside the container. So that's the partial pressure for gas 2. Partial pressure of gas 1, the number of moles inside the container, that's of gas 1, divided by the total number of moles inside the container. You multiply that fraction by the total pressure inside the container. Okay, so you add up the total partial fractions, you add up partial pressure of gas 1, partial pressure of gas 2, so on and so forth, you'll get the total pressure. So let's do that problem. Okay, this will make more sense once we do a practice problem together. So a sample of natural gas contains 8.24 moles of methane, CH4. Okay, this is the number of moles. The number of moles is N. Okay, 0.421 moles of ethane. Okay, so we'll call methane gas 1. Number of moles of gas 1, methane, N1. 0.421 moles of ethane, we'll call it gas 2. Number of moles of gas 2, ethane, C2H6. And 0.116 moles of propane. Okay, 0.116 moles of propane, C3H8. That's gas 3. The number of moles of gas 3 propane is 0.116. If the total pressure of the gas, the whole thing, which would be methane, ethane, and propane together, that total pressure is 1.37 atms. Okay, what are the partial pressures of each individual gas? Okay, so we'll just go ahead and utilize this formula here. Okay. So first we have 3 gases. Okay, just like in this drawing, 3 gases. Excuse me. All right, we'll do the partial pressure of CH4, which is methane. Okay, the P stands for pressure. Okay, we've got 8.24 moles of methane. Okay, what's the total number of moles? The total number of moles is, what's 8.24 plus 0.421 plus 0.116? Uh-oh, I don't have my calculator. I think you'll come to my rescue here. 8.77, Emily. We'll take 8.24 plus 0.421. Awesome, thank you so much. Moles total. And then what's the total pressure at 1.37 atm? So what is that on our calculator? Oh, I do have a calculator here. Yeah. Okay. Thank you, though. Good student. Okay. Helping me with the calculations. I appreciate it. And I appreciate you as well, just being there. 8.24 times 1.37. Okay, divided by 8.77. About 1.29 atmospheres. Okay. The moles cancel. I'm getting about 1.29 atmospheres. That's the partial pressure of CH4. Okay. How about the partial pressure of C2H6? Let's do that one together. Okay, this is called ethane. Okay, this is 0.421 moles. And our total volume, the fraction of this is 8.77 moles total. And the total pressure is 1.37 atm. Okay, so what is this on our calculator? We'll take 1.37 times 0.421. Divided by 8.77. And about 0.066. We'll do 0.0657 atm. Okay, and then finally our last one here is propane, okay, which is C3H8. The partial pressure of C3H8 is going to be 0.116 moles of C3H8. Okay, our total is 8.777 moles, and then we multiply that by the total. And let's do this, 1.37 times 0.116, okay, divided by 8.77. I'm getting 0.0181. Atmosphere. Okay. And this is the answer. Right, so if I take 1.29 plus 0.067657 plus 0.0181, okay, what will that equal to? If I add those three partial pressures up, what will I get? Let's do that. 1.29 plus 0.0657 plus 0.0181. I get 1.37 atm, and that's my total pressure. You see that? the individual partial pressure sum up to the total pressure inside the container. So there you go. Okay, out of 1.37 atmospheres, 1.29 atmospheres are exerted by CH4 methane, 0.0657 atmospheres are exerted by C2H6, and then finally 0.0181 atmospheres are exerted by C3H8, which is propane. So that is how you do a Dalton's Law of partial pressure problem. We got 3 more pages to go, so let's go ahead and finish this up, then we'll do our little test review for today and then tomorrow as well. Alright, so the speed of a gas is not one speed, as it's called. It's actually called by a different term. It's called root mean square speed. Okay? Because let's say we are an oxygen gas. You're an oxygen, I'm an oxygen gas, everyone here is an oxygen gas. I, as an oxygen gas, may diffuse faster than you, Emily, as an oxygen gas. Why is that? Because you collide with something else. You collide with the wall of the container. Every oxygen gas in this container of oxygen gas will have different speeds because they'll have different diffusions, different collisions, different everything. Each oxygen gas will have its own, experience in terms of its diffusion. Remember, we say gases diffuse. So this collective number, this one number that collectively describes the motion of all the oxygen gases is called the root mean square speed. Okay, it's called U, and then at the bottom we'll put RMS for root mean square speed. It's not like I drive down Ramsey Street at 35 miles per hour. Okay, I, as a gas, oxygen gas, for example, will diffuse a little faster because I have less collisions. You, Gerardo, may diffuse a little slower because you just collided more by diffusion. Every oxygen gas will have a different speed. Okay, collectively that number is one number, root mean square speed, and the equation is actually right here. Okay, so I'll give that to you on an exam. So we have R, which is the gas constant. This is a different gas constant. I'll give you all the constants in the exams. So this one is 8.314 joules over a mole Kelvin. This is another gas constant. There are several different gas constants. This is the one you're going to use for this equation. And that's R. T is temperature, which must be in Kelvin. And then molecular weight is the molecular weight, but interestingly enough and importantly, okay, it's not in grams per mole. Okay, it must be in kilograms per mole. So this J, do you know what J is? Just J means joule. We'll talk about this later on. J is joule, which is a unit of energy. Okay, we have not talked about it. We'll talk about it in chapter 6. 1 joule is equal to 1 kg meter squared per second squared. This is called a derived unit. Okay, all the math and engineering people may know, I think, derived units. So 1 joule is a kilogram, which is the SI base unit for mass. Meter, SI base unit for distance. We square that divided by the base unit for time, which is seconds. That's also squared. Okay. So our final units here for speed, what do you think the unit of speed will be? Anybody here have taken physics before? The units would be meters per second. Okay? For a gas, meters per second. Oops, sorry. Okay, if we're driving my car, or your car, it'd probably be miles per hour. But here, in this context, it's the distance is meters, the time is in seconds. You guys coming to work today, or school, or me coming, the distance is miles, the time is hours. Okay? Yes? Okay, so this is speed, but it's called root mean square speed because, once again, every oxygen gas, every nitrogen gas, every fluorine gas, every CO2 gas will have a different speed. So that one collective speed, that one amalgam, that one everything of all the different speeds is the root mean square speed. All right. And so it's not one speed, okay? It's a distribution of speeds. So here's N2 gas, which has a molecular weight of 28.02 grams per mole. Okay. And at 100 Kelvin, remember in gases everything is in Kelvin. Okay. This is the distribution. This is the highest point of the distribution. Okay, at 300 Kelvin, this is the distribution. And this is the highest point of the distribution. Okay, and then finally at 700 Kelvin, this is the distribution. Okay, this is the highest point of the distribution. Okay, what do you see happening as you go from 100 Kelvin and you increase it from 100 Kelvin to 300, and you increase that from 300 to 700. Okay, what's happening to the distributions? Go ahead. Okay, the amplitude or the height is going down, but what else is happening? Okay, there's more gas molecules that are these higher speeds. Okay, look at this tail here. Okay, at 700 Kelvin, you have more gases that are going this fast. Okay, right? So what does that tell you about temperature and the speed of a gas? What does this tell you or tell us about the temperature and the speed of a gas? If you increase the temperature, what happens? The gas molecules will go faster. Okay, you see that right here at 700 K. You have more N2 molecules experiencing speeds of up to 1,500 meters per second, 1,000 meters per second. So one take-home point here is that as the temperature goes up, the root mean square of the gas goes up. You actually see the temperature in the numerator here. So we say the temperature and the root mean square speed of a gas is directly proportional, directly. As temperature goes up, what else goes up? The speed. Actually, we call it root mean square speed. Okay, so that's a direct proportion. As one goes up, the other goes up. I'm going to say URMS. So what is this called? Okay, on any multiple choice or any part of the exam, we call this a direct proportion, directly proportional. Okay, direct proportionality. All right, now let's look. So this is temperature. Effect on root mean square speed. Let's look at mass. Okay, let's look at mass. Okay, so let me see if I can zoom in here. All right, we have here chlorine gas, which is about 70.9 grams per mole. Okay, well, this is its speed. Okay, and this is the speed profile. This is the height of that speed profile distribution. Okay, we'll increase the molecular weight of the gas from chlorine and change the identity to nitrogen. whose molecular weight is 28.0 grams per mole. And this is the distribution. This is the height of that distribution. And then finally, we're going to change the identity of the gas to helium. Helium has a molecular weight of 4 grams per mole. And this is its distribution, and this is the height of that distribution. Okay? So what do we see here as we go from 70 grams per mole to 28 grams per mole to 4 grams per mole? What's happening? Okay. The lighter gas has, what is this? The lighter gas experiences more speed. Okay? It's a whole distribution. What happens if we increase the mass of the gas? Going from chlorine, heavy gas, nitrogen, kind of heavy gas, helium, very light gas. What happens to the speeds? The height decreases, but what about this? So the lightest gas, helium, at 4 grams per mole, can experience speeds of, 2,500 meters per second, 2,000 meters per second. Okay, the lighter the gas. Okay, so what is the relationship between molecular weight and root mean square speed of the gas? Okay, as the molecular weight goes up, okay, what happens to the root mean square speed? If you're really light gas, really light, it gets what? As the molecular weight goes up, what happens to your speed? Who's fast? Who's fast? A big. Who's faster? A track athlete? Anybody here play track? Or not play? Participate in track? Nobody here's a track athlete? Okay. Who's faster? A big guy like me who's 200 pounds, heavy, or a track athlete who's, 160 pounds? Who do you think is faster? Okay, obviously me. Oh, well, thank you again. I appreciate the compliment. Maybe if I was your age. I used to do stadium steps. I used to jog the stadium steps at my school. So, at that time. But reality is that a track athlete who's very lighter is faster. Okay, so as the molecular weight goes up, as the mass goes up, what do you think the root mean square speed of a gas would be, up or down? Down. Okay, as one goes up, the other goes down. This is an indirect proportion. Okay, indirect proportion. So as in terms of testing or multiple choice, okay, one goes up, the other goes down. This is an indirect proportionality. Okay. All right. So, a lot going on here. Okay, the speed of a gas is not actually a speed. It's a diffusion, because every gas molecule will have a different experience based on collisions. And so the collective speed is sort of enveloped in this equation. Okay, we have a different value of R, and your molecular weight must be in kilograms per mole. When you put all of that into this equation, the final units of speed are going to be meters per second. Okay, some distance, in this case meters, over time, in this case seconds. Your speed coming to school today was miles, which was the distance, over hours, which is the time. Okay? Distance over time is the final units here for this equation. Okay. All right, let's do the last 2 pages here. I'll just go ahead and skip to page 13. Okay, so there's 2 things I want to talk to you guys about. Okay, so you look on page 12, we have diffusion and then we have effusion. Let's describe the differences between these 2 here, diffusion and effusion. Okay, so diffusion is kind of like this. Okay, this kind of zombie-like moving of the gas molecule. Okay, what causes it to change direction? Okay, a collision between another gas molecule or a collision with the side of the container. Okay, now effusion is a little different. Imagine here's the container, right? Okay, so here's the same container. And I'm going to put a tiny, tiny pinprick hole. Tiny, tiny hole. Okay. So now this same gas molecule, okay, actually goes out of this hole in a straight line. Okay. So this is an opening. So now we have diffusion, but we forced it to be linear by putting this small hole. Okay, make sure the opening is big enough for the gas to go through. If the opening is small enough, the gas can't go through. Okay, so the pore or the opening should be large enough so that the gas can come out. It will come out in a straight line. Okay, so that is what effusion is. Okay. This effusion is a time. So we say effusion time. And this diffusion is a rate. Okay. It is a rate. Okay. So how much distance over time. Okay. Okay, this time is a time. Meter, minutes, seconds, hours, days, years, whatever. Okay, so this is distance over time. This is just a time. Right, so that's the difference between diffusion and effusion. Okay, we take the container, we take the balloon that's filled with gas or whatever it may be. We're going to do a little pinprick, and the gas will start seeping out. It will seep out in a nice straight line. That's effusion. We say an effusion time. Diffusion is just how gases move. Okay, they zombie around, they collide, they hit each other, they hit one another, they hit the container. That's a rate, how fast that is. Okay, usually, if you remember our previous equation, it was a root mean square, which was meters over second. Okay, some rate. All right, so let me give you the equation for this here. Okay, so if we're talking about effusion, okay, the time of gas 2 or time of gas 1, this equation is on page 12, by the way, okay, is equal to the square root, this is a ratio of the molecular weight of gas 2 over the molecular weight of gas 1. So this is the equation for effusion. Okay, and our equation for diffusion is this. Okay, it's a rate. Okay, so this is a time. Okay, so rate 1 over rate 2 is going to equal to the molecular weight of gas 2 over the molecular weight of gas 1. Okay. It's really the same equation. It's the ratio of the square root of the molecular weight. Okay, square root. Okay, so notice the flip. Okay, T2 here for effusion, rate 1 here for on the numerator for diffusion. Okay, so these are the equations. I'll give you these equations on the exam, so you do not have to memorize them. Just make sure you know how to apply them. Okay, as they call it, plug and play. You heard plug and play. Okay, plug it in and get get the answer out. All right, let's do this problem here. That will finish this chapter, and then we'll go over the test review. All right, it takes 192 seconds for an unknown gas to effuse through a porous wall, and 84 seconds, so this T1 at 192 I'll call 192 T1. This T2 at 84 I'll call it time 2, T2, for the same volume of nitrogen gas. Okay, let me read that again. 84 seconds for the same volume of nitrogen gas, so I'm going to call that gas 2, okay, or molecular weight gas 2. For T2, I'm going to call unknown gas gas 1. Okay. Is that all right? Okay, gas 1 is unknown. Okay, gas 2 is nitrogen gas. The effusion time for that is 84 seconds. The effusion time for unknown is 192 seconds. Okay, what is the molar mass of the unknown gas? Okay, so we want the molar mass of the unknown. This is the information that we have here. So which equation we'll use? We see it. We have a time here, so we're talking about effusion. Okay, we also have the word effuse. Okay, so let's use this equation from our notes. All right, so what's time 2? 84 seconds. What's time 1? 192 seconds. What's the molecular weight of gas 2? Nitrogen, it's about 28.02 grams over a mole. Okay, we're just plugging it into this equation, which will be given on the exam. Divided by the molecular weight of the unknown gas. That's what we want to find out. Okay. All right, so to solve for the molecular weight of the unknown gas, we will square both sides of the equation. All right. Oh, by the way, the seconds cancel. So 84 divided by 192, okay, squared. If we square this, it removes the square root. This is still grams per mole, by the way. And this is also grams per mole. All right, so the molecular weight of the unknown is going to equal to, I'm going to cross multiply. All right, so the 192 squared times the, let me just remove this grams per mole. I don't want to make things confusing. That's fine. Just remove that. We'll put the units at the end. Okay, 192 squared times 28.2. Cross multiply this, okay, times 84 squared. Okay, so cross multiplication gives us this. Okay, I cross multiply. You remember cross multiply from math? Right, so the molecular weight of the unknown is going to be 192 squared times 28.02. Excuse me. Okay, times 28.02. Okay, we'll divide this by 84 squared. 146 grams over mole. Don't forget the units. Okay, so this is the number I'm getting, and that's 146 grams per mole. Okay, that's the molecular weight of the unknown gas. Okay, so don't forget the units here. Okay. Grading some exams, not for this class. Chem 2 and students were not putting the units, or they're putting the wrong units. Okay, so put the right units. Okay, the units of molecular weight are grams over a mole. Okay, units for time, seconds, minutes, hours. Units for rate, miles per hour, meters per second, some distance over time. Okay, units are very important. All right, are we good with this? So effusion time is related to the molecular weight according to this equation. How fast a gas diffuses is related to this equation. And of course, one more equation that I'll also give you is the actual speed of a gas. We call it root mean square speed. And that's 3RT divided by the molecular weight, all of that under the square root. Okay, so those are the three equations involving gas speeds and effusion times, diffusion rates. So these are the three equations. We'll give you those those three equations on the test. So that is a wrap of Chapter 5. So let me pause this and let's go ahead and do a little bit of our test review, and then we'll finish the test review on Thursday. Let me just get myself settled.